Hello, my name is Antonio Torija Martinez, professor in Acoustic Engineering and Psychoacoustics at the University of Salford in Manchester in the UK. I would like to start thanking the organizers of this very interesting event for the invitation. Today I'm going to talk about progress and important gaps in the measurement and assessment of drone noise. I'm going to start my presentation describing some background about drone noise. So we have evidence suggesting that drone noise is perceived as more annoying than the noise produced by other vehicles for the equal loudness. You can see this in both pictures here in the diagram in the slide. So you can see on the left hand side that for the same sound exposure level, drone noise was perceived as more annoying than cars. This was a study developed by Andy Christian in NASA a few years ago. And also on the right hand side you have some ongoing results, preliminary results in terms of exposure response curves for highly annoyed people for drone noise compared to other vehicles. And as you can see there, for the equal sound exposure level, drone noise tends to be perceived as more annoying than the noise from other vehicles. Well, we have some hypotheses why this might happen. In principle, we know that there is a significant high frequency noise produced by drones. We know that the blade passing frequency is relatively high and the harmonics compared to other rotorcraft. We have a lot of high frequency noise due to motor noise, particularly some tonal noise about 3.5 kilohertz, as you can see here in these spectrograms. And we also know that drones or these vehicles are relatively small and can be highly affected by weather conditions, for example wind gusts. In that case, the noise signature of the vehicle is significantly affected, and that's going to have implications from the noise emission point of view, but also from the psychoacoustic point of view, how that noise is going to be perceived. And as you can see, when you have complex wind conditions, you can see the vehicle changing the rotational speeds of rotors, trying to maintain the stability of the vehicle. And in that case, you can see how there is some unsteadiness in the signal as presented here in these tonal components. And finally, we also know that drones and other eVTOLs will have significantly different operational procedures. They have some unconventional procedures, for example, taking off, hover, transition to forward flight, etc. And that's going to add complexity to the problem. Also, these vehicles are going to fly close to the ground compared to other rotorcraft or aircraft, and therefore we might need to take into account also what is the influence of the ambient noise in terms of how these vehicles or the noise from these vehicles is going to be perceived. Now I'm going to move on to talk about some state-of-the-art in drone noise measurements, with a particular focus probably to what is being done or what is proposed to be done here in Europe by EASA. Well, in 2019 we probably had the first regulation about drone noise. It was a Commission delegated regulation 2019-945, and in that case it was applicable for drones of the open category up to 25 kilograms of maximum takeoff mass. In this case it was all based on measurements in semi-anechoic chambers following the ISO 3744 from 2010 to measure directivity. To measure sound power level, directivity was not considered, and in that case the operation was hover about one reflecting plane. And then the regulation presented or suggested some maximum sound power levels in decibels for drones of the category C1, C2, up to 4 kilograms, depending also where those vehicles were entering into service. After that, EASA here in Europe published the guidelines on noise measurements for unmanned aircraft systems with weight lower than 600 kilograms of the specific category, in this case with low and medium risk. In this case, EASA proposed noise metrics for the measurement of flyover operations, and in this case it is A-weighted sound exposure level. For hover operations, A-weighted equivalent continuous sound exposure level. One of the potential limitations of these guidelines is that there is also the requirement to use one single microphone, as usually done in aircraft noise, in an inverted position, so that the microphone diagram is 7 millimeters about and parallel to a ground plate. And also in these guidelines there is special focus on monitoring and the spatial positioning and speed of the drone, and they propose different methods to monitor this. The Urban Air Mobility Noise Working Group of NASA has also been working on this topic, and specifically on developing a measurement protocol for the creation of noise spheres or hemispheres that describe the vehicle source emission characteristics. In this case, the idea is to record acoustic pressure, time histories, to capture also spectral information. What they propose is the use of microphone arrays, like for example 11 microphone arrays, ground-based in inverted position, as recommended by EASA as well. But in this case, the plan is to have a perpendicular microphone array perpendicular to the flight path of the drone. Okay. And finally, we have the ISO 5305 published in 2024 on noise measurements for unmanned aircraft systems. In this case, they consider, or the standard is applicable for drones, vehicles up to 150 kilograms of maximum takeoff mass. The consideration or the measurements are for far field only. The objective is to capture their activity characteristics, of course. So the idea is also to generate some noise hemispheres or spheres, complete spheres. There is also methods proposed for 3 test areas: anechoic chamber, wind tunnel, and outdoors measurements. And here they expand the EASA guidelines, which only consider cruise and hover. And in this case, the ISO standard also provides methods for takeoff and landing operations. And the microphone array for outdoors conditions is similar to the NASA Urban Air Mobility noise guidance. Well, at Salford, in my group, we have been carrying out several measurements. In this case, following completely aligned with the EASA NORAD model. In this case, using a microphone array of 9 microphones covering emission angles from -60 to +60. In this case, azimuthal angle, and in this case we have a microphone array perpendicular to the flight path. And here in the picture you can see our experimental setup, measurement setup, with the microphone in an inverted position with the diaphragm at 7 millimeters from the flat plate, as is expected. We also bring anemometers to monitor wind conditions, and also we keep positioning and operating conditions of the vehicle as well. Once we have our measurements, what we do is we back propagate from the microphones on the ground to an arbitrary distance from the source. We do that accounting for the main propagation, sound propagation factors, which is the distance between source and receiver, atmospheric absorption, ground effects, and also we do a process of dedopplerization in order to remove the Doppler shift in the measurements. And this is because we want to produce noise hemispheres containing only the information about the source and not the noise propagated to the ground. So far at Salford, we have 5 comprehensive measurement campaigns. We have measured many different vehicles from multi-rotors with single and coaxial rotors. We have also measured vehicles with new designs for propellers in collaboration with the University of Manchester. We have measured vehicles from 1/4 kilo to over 100 kilograms with number of rotors 4, 6 and 8. Diameter of the vehicles from about 30 centimeters to almost 3 meters. And also we have measured operational conditions, takeoff, hover, flyover and landing. The method in our case is multi-channel acquisition system, as I said before. And for anyone interested, we have put together a drone noise database that could be accessible using this link here in the slide. So the way we work here at Salford is, once we have our measurements of particular drone, what we do is following a process of spectral analysis to define the source in detail. So we extract the tonal and broadband information and to define the source better. We extract information about modulations, which are also very important for drones. So once we have the source defined at an arbitrary distance from the vehicle, what we do is a process of sound propagation in order to analyze the signal, so we can present that sound to participants, for example, if we are doing listening experiments. And we can do those listening experiments in specialized rooms we have in our group. For example, this one you can see in this picture, when we have an ambisonic speaker system in order to have an immersive presentation of sounds. I'm going to continue now talking about the progress on drone noise assessment. Well, looking at conventional aircraft, we all know we have well-defined procedures. For example, we have 3 measurement points for aircraft noise: approach, sideline, and flyover points. We know that for aircraft certification we use metrics like EPNL, effective passive noise level, and also we use sound exposure level as well for helicopter and propeller aircraft. In the case of drones, the operational conditions, as I said before, are different. We have measurement conditions like hover, or we have measurements conditions operations like cruise. And in this case, EASA here in Europe recommends LAQ for hover and sound exposure level for flyovers. However, for drone noise, we know that loudness is probably the main factor driving responses in terms of drone noise annoyance. So metrics like sound exposure level would be appropriate. But in the case of drone noise, we also have some other important factors to take into account, some other psychoacoustic factors to take into account. Like, for example, the presence of high frequency or sharpness, the presence of discrete tonal noise or tonality. Sometimes we have the sound to be of impulsive character, and sometimes we have some interaction between rotors leading to situations of amplitude modulation, and in that case we can use metrics as fluctuation strength, or even we have this unsteadiness in the signal due to wind conditions, and we have metrics, for example, like roughness that could help capturing that phenomenon. The other things we know as well is that transient operations like takeoff and landing tend to be perceived as more annoying than flyovers. For the particular case of drones also, I've been talking about that we have measured drones for about 1/4 kilo to over 100 kilos. And something interesting we have found is that loudness seems to correlate well with annoyance for drones with takeoff mass about 4 kilograms, as you can see here in this red line in the diagram. However, for drones, for small drones, probably below 4 kilograms. In that case, you tend to see that the annoyance produced by those drones tends to be independent or not correlated with loudness. And in that case, we have other important metrics to bear in mind, like, for example, tonality or sharpness, etc. In that case, what we have done in my group, and this is a PhD student, Nathan Green, is developing a new formulation to predict annoyance due to drone noise, where we establish this type of relationship, where we take into account loudness, and also we take into account tonality, roughness, and a new metric which is called relative approach, which takes into account the unsteadiness of the signal. And if you have different coefficients for these metrics based on as a function of the weight of the drone, or in that case different coefficients for drones lower than 4 kilograms and drones with weight higher than 4 kilograms, in that case you can have a really good expression to predict noise annoyance due to drone noise, regardless of the size of the drone, in a very accurate way. Other thing we know, and this is work developed by NASA, specifically Siddhartha Krishnamurthy and Andy Christian and other colleagues, is that the presence of ambient noise can reduce the annoyance due to the drone operation, due to the noise produced by the drone. And this is because the ambient noise can act as a masker of the signal, of the drone noise signal. And therefore, NASA has developed an expression to take into account or to estimate annoyance, but annoyance only due to the drone when you discount the presence or the effect of the ambient noise. And therefore, with this method, what you can do is just you can create maps for the noise annoyance for a given operation, in this case a drone or eVTOL, etc. But when you discount the effect of the ambient noise, so you only consider the effect of the specific drone or eVTOL. In my group, we have found something similar. In our case, in a psychoacoustic study we did for drone noise in the presence of ambient noise, park and street, we found that the detectability of that drone, or in other words, the prominence of the noise of that drone noise over the ambient noise, is highly correlated with the changes in annoyance when we ask participants of that study to give us values of annoyance when the ambient sound was alone and when the drone was also present. So you can see this clear trend here between the detectability of the drone and changes in noise annoyance. Well, so this is something we are considering in the development of psychoacoustic models in order to estimate annoyance due to drone noise. I would like you to focus only on the column in the middle of this table. So we have developed different models to predict noise annoyance due to drone noise. And in this column, you can see some of the variables we are considering. In this case, we're considering the loudness of the drone. We also consider the ambient sound level, so the sound level present in the area where the drone is operating before the drone operates. We also consider sharpness, which is a metric accounting for the high frequency content, and also we consider tonal loudness, which is a metric accounting for tonality. And finally, we consider the number of events, of drone events in the area. So with that, we have developed very sophisticated models able to predict the percentage of highly annoyed people due to drone noise operating in a given environment. And again, I want you to focus on the diagram on the middle, which is the results of the model I mentioned in the slide before. And in this case, you can see that we are able to predict a highly percentage of annoyed people due to their noise with an R-square of over 0.8, which is very high. I would like to finish my presentation very quickly talking about important gaps still to be addressed. So an important thing is that we have a lot of regulation in terms of how to measure drone noise, but still we don't have noise limits. For example, in the ASA guidelines, that section is empty and is reserved for further development. Another important gap is that we don't have a comprehensive database of drone noise with noise hemispheres operating for different operating conditions, and also we don't have optimized modeling tools for drone noise, as you can see. I would like to finalize acknowledging the funding provided by my research for the drone noise, RefMap and Mafusa projects. I'm sorry I won't be able to be there with you for this important event, but I will be happy to answer any questions you have. If you have any, please send me an email and I will respond as soon as possible. Thank you.